Okay, thank you. Good. So welcome to my second talk of the session. Skip ahead a bit. Okay, so here's the quick motivating example, right? Okay, so we can plot these on like the Euclidean plane by two axes. One is the extent to which these data points have tried to kill me, and one is the difference between the number of ears and the number of eyes in these various data points. So it's very compelling. And here's one natural way to cluster them into two clusters. You might think that one of those data points maybe belongs in the blue cluster, but I do approximation algorithms. Okay, so some popular problems. So okay, so this is just the notation. So we'll have x is a finite point set, d is the distance function, and k will be the number of clusters that we want, right? And then we want to choose k centers in our data set. So there have been a lot of talks on Euclidean settings. Here we're just talking about a general metric space. So I'm not assuming that the metric is Euclidean, right? And then we just want to pick points from x and assign all points to the nearest center, right? And then we have like possible minimization objectives. So there's right k median, the sum of distances, k center is the maximum, right? And k means some square distances. And you can also think of these as, right, already mentioned in all these talks, right? But, right, so in fact, these are just the L1, L infinity, and L2 objective, or the L2 objective here is squared, but these are all various LP objectives, okay. Right, and so, some of these problems are all hard, but they can all be approximated well, so probably this slide is, you've also seen in a number of talks already, and they all have some hard. So they all have a constant approximation. They're all APX hard, and I just so I think these are all the current state of the art, unless I'm missing something. And the reason I mentioned for K median the slightly older result of TRAC et al. Is that we actually make use of some piece in their algorithm. Not just for K median, for our general problem, but we sort of use this within our algorithm. So I just wanted to get that out there. Okay, so right, obviously very well studied, but clustering, which we think of as good by these measures that we talked about, is not necessarily fair, right? What is fair? So for example, if you think of like, you have, you want to sort of assign people to vaccination centers, and you have isolated communities. So, maybe sort of the average person is very happy and has a nearby place they can get a vaccine. But, maybe if some people are like, left out in the cold, then it's not, maybe it's a globally good clustering, but not very fair to isolated people, right? So here's an example, a little bit more abstract. And we have this group of green diamonds and group of brown diamonds. Right, and so what we call a p-fair clustering it is a clustering, same definition as before, and we have these groups which are like sets of points, subsets of our point set, and now our objective is again an LP cost objective, but rather than just taking like the global LP cost, we look at the LP cost just within every group. So for example, we look at like the LP norm of the cost vector for the green points and for the brown points, and then we just look at the worst one, right? So we take the maximum, right? And here, don't stare at this formula too long, but this is, right? So the cost of GI is like the group cost, and then we want the maximum over all of these groups. Okay. So, right, this is known. There's a recent result of Makarchev and from Code 21, which gives this approximation for any p. And also this approximation is known to be optimal unless NP is solvable in sub-exponential time. So that's it. So the problem is solved. Thank you for coming to my talk. not give the third talk. Okay, so no, there's more, obviously. So you could ask, why take the maximum over all the possible groups, right? It could be different, except for all these very good reasons to take the maximum. But, what about a kind of more general notion of fairness? Why is this the right notion? Actually, sort of focusing in this sort of extreme way on fairness may take us very far away from global optimality, right? So we might want to sort of balance them. And one way to balance them, right, is if, okay, oops. Okay, good. Okay, so one way to balance them is this more elaborate notion of PQ fair clustering. So we still have these LP costs per group, right? So the input is still the same, but now instead of taking the worst possible group in our solution, we look at the vector of group costs. So we look at all the group costs and we look at this vector of costs, and then we take the LQ norm of that as opposed to the maximum, which is the L infinity norm, right? So when Q is infinity, right, that's the L infinity norm, that's the P fair clustering that we talked about before. And right, when Q is equal to P, then that's just plain old, global optimization. And if you kind of, if you move the needle between these two extremes, then you can have sort of like a softmax or something in between that kind of weighs fairness against global optimality, and you can decide how far you want to go between these two possible objectives. Okay. All right. So what do we show? So here are our results. We have a general approximation algorithm which applies for every setting of parameters with Q between P and infinity. When they're both constant, then we get a constant approximation as it matches the constant approximations for K means and so on. And in the other extreme case for P fair clustering, which is when Q is infinity, take the maximum of over all possible groups, we get the same approximation ratio, which, as I mentioned, is optimal as the previous result. So just a reminder of what that was. And in general, this is the expression, right? So this expression, is O of 1 when they're both constant. And I know that when Q is infinity, it looks like it's infinite, but then you have to consider that actually, L infinity and L log n are equivalent in dimensions. So, so if you plug in Q equals log n, you get don't do it in your head because your attention span for the rest of the talk. Okay, so so very quickly, right? We sort of follow the usual lines in approximation algorithms. So we have this 0-1 program, and then we relax it to a linear program, right? And then we know that we round the optimal solution to the linear program, and then we bound the loss in the rounding, and we get an approximation algorithm. So, just sort of putting this bullet points so that we can sort of follow along in the talk. So we're going to have sort of three main goals, right? One, formulate the right LP relaxation. Two, design the right rounding algorithm. And three, analyze it and show that found the loss in that. And I should mention, because this will also come up later, that we don't necessarily, and actually we won't rely only on linear programs. Actually, here we do, but in general, the constraints don't have to be, all right, so in general, the constraints don't have to be linear, they can be convex, which might be a little bit better. And in fact, the only thing we require, right, is not even, the only thing that we require for these convex constraints is that we have a separation oracle, right? So just a way to identify violated linear constraint, and then we can right, then we can use the ellipsoid algorithm. And so on. Okay, so I'm sort of harping seemingly needlessly on that, but I just want to get back to it later at the talk. Okay, so all right, so we have a simplified setting, which comes from this paper that I mentioned before of Chadka for K-median, which works equally well in our setting. And this is a kind of reduction that they do from, which takes you from sort of the general clustering input to this very specific format where you have these two disjoint point sets. And your task is now to choose for some parameter which arises in the reduction, some number of points within one side, within A, to be the non-centers. Okay, so everyone else is going to be a center, and there's just a specific number of points within A that will not be centers, and then they're going to be assigned to their nearest neighbor, but not globally, but on the other side, their nearest neighbor in B. So this becomes like almost a kind of matching problem. This becomes like a much simpler setting. Okay, so we have a certain number of points we want to choose in A, and they're going to be assigned to their nearest neighbor in B. Okay, and then and everything else is the same. The objective and so on. We haven't changed anything. But right, so now the group costs are like the group costs induced on this new instance. Okay. Don't worry about the formulas too much. Yeah, of course.
Your non-setters are going to be assigned to the nearest point in B, or
in B, yeah, they're going to be assigned
to the ones that you pick.
Right, not their nearest neighbors within the whole input, but only in B. So this makes it a little bit easier. You don't have to worry about, wait, if I decide that this is a non-center, I can't assign someone else to this, you know, and this kind of avoids these conflicts. So this becomes a much sort of cleaner problem.
So can I ask something?
Yeah.
Looking maybe at the formula that you had, and maybe this is something you mentioned, but I missed. Do you assume anything about Q and P? Which one is larger?
Yeah. So Q is greater or equal to P in this setting.
Is it just because this is when your method works, or it somehow seems to be?
Okay. So it's the one that sort of corresponds to the motivation I've given so far, but we also have algorithms for the other setting, which I'll talk about a bit towards the end of the talk. But they're very different, and also the complexity is very different. It becomes a very different problem. Okay. So
yeah. Is it important that the groups be disjoint, or you don't?
Oh no! Oh, sorry. No, the groups don't have to be disjoint. Other questions? Okay. Okay, so we have sort of the convex program that you would expect. You don't have to read through it because I'll walk you through it. So, right, so the objective function is the aggregated cost. It's exactly what you would expect. And then we have the first constraint represents the group costs. So these ZIs represent the group costs raised to the Q. Just for convenience, and or because that makes this convex. And then the final line is just the size constraint, right? It's the one saying that this is the specific number of points that we want to pick as non-centers in A. Okay. Okay, so we have exactly the convex program that you would expect, right? And because Q is greater or equal to P in this setting, then this constraint is convex. Right, and the first one is not, but you know, it's equivalent to a linear constraint. So just think of it as a linear object. Okay, so where are we in the talk? We have the convex relaxation, so we're 1/3 of the way through. So now let's talk about rounding. So right, we do sort of the simplest rounding that you can imagine. We look at every point in A, and then with probability, you know, which is the value assigned to it in the convex program. With that probability, we decide to add it to the set independently. Okay, so now we're 2/3 of the way through, and now we just have to analyze it. So here's the analysis, and just a quick caveat. So there's going to be I'm going to lie to you somewhere in this in these next couple of slides. Not this one specifically, but then I'll tell you where. Don't worry. Okay. So first, let's analyze the solution size of the number of points that we choose. So this is right. This is just a plane of linearity of expectation, and because this expectation is large, then Chernoff dictates that with high probability we will be very close to the right number of points. So that's not a concern. Okay, so we're done with the solution size. Now the cost per group. Okay, so the cost per group, right? So we're looking at the distances from points to the centers they're assigned to raised to the p and summing those up. Right, so again, we have linearity of expectation, and then Chernoff and concentration, and move on. Sorry. So right, so the expression we get is again the cost, and it matches what we have in the Convex program. And then finally, we look at the aggregate cost, right? And by what we just showed before, the aggregate cost is going to be concentrated around, the objective function. So it seems like we just solved the problem exactly, even though it's NP hard. So I definitely lied somewhere. So let's see where I lied. Okay, so it's obviously it's the group cost, right? Because the first one was just okay. So this much is true, right? You have linearity of expectation, it's a thing. But you don't have concentration, right? Concentration, you only have concentration in the right setting. Like you have to have, summation of Bernoulli variables with very large expectation. If the sum of the expectation is very small, then there's no reason to have concentration. You could just have something that's one with very low probability, and otherwise zero. It's not going to be concentrated. Okay, so when does the rounding fail? So here's a very simple example. Let's think of all the distances as one, just to motivate what the issue is. And let's say we don't have this concentration. So we have this rounding, and then what happens is within every group, the contribution in the objective function is very small. It's like little o of 1, right? So we're not going to have concentration. It's going to be 0 most of the time, and with, let's say, probability epsilon or so, it's going to be 1 or something very small, right? So I won't do all the math, but if you sort of do this very quickly, you see that the approximation ratio is going to be very bad, right? Because you won't have concentration, you have these very low probability events, and then then you have this big gap between what the rounding does and what the Convex program claims you should be getting. And right, so for arbitrarily small epsilon, this will be unboundedly bad. Okay, so how do we fix this problem? So we concentrate again just on this.
Just one quick question. Are you worried about concentration of ZI around this expectation, or the sum of ZIs around this expectation?
No, there's ZI specific.
Because that's the cost per group.
Yeah, the cost per group is going to be very far in the rounding from what the Convex program claims it should be.
But eventually you only care about the sum, right?
Yeah, but they could all be bad. They could all simultaneously be bad. Yeah. Or you could just have one group and that group is bad. Okay, so so the problem, we're not really capturing this here, right? Because this is kind of, this is not the right measure, right? This works when there's concentration and when the sum is large, and if it's not, then it's bad. So it turns out that here we're actually better off just using a linear bound, which behaves better when the right? When there's only a very small probability of getting any points in this group, right? And the proof is actually it's just monotonicity of norms. It's not complicated. Right. So so how does this help us? So we can just add this constraint, right? We can add this constraint and just add this additional bound of saying, it's lower bounded by the relaxation of the one norm instead of the Q over P norm, which it seems kind of, sort of maybe meaningless, but actually in this context, it helps. This is exactly what we need in order to handle these low concentration cases, right? So if all groups have high concentration, or all groups have, or no groups have high concentration, then you can show that the rounding works by just plugging in, whichever of these two constraints is appropriate. But that it's not clear from just kind of this straightforward analysis that if you have like a mixed case, that this will work, right? Because the analysis is a little bit different for the two cases. So who says that just having a constraint to deal with high concentration everywhere and low concentration everywhere is enough? This guy says that it's enough. This is Rafael Latawa. And he has this nice inequality in our context. Basically, it says that exactly what you need. That if you have this, expectation of these, this norm of independence of sums, then it behaves in the way that you want it to behave. Right. So this first part deals with the high concentration groups, and the second part deals with the groups where you have only a very low probability of choosing any point, and both of these are bounded by our constraints. And then the thing on the left, that's before the multiplication. That's exactly our approximation factor. So that gives us the approximation factor. Yeah.
I mean, maybe it's a very simple question, but is this like, this Natala's thing of using various norms to look at the worst norms to get a concentration? Is it a little like in basic Bernstein or Chernoff bond, you have a variance term and then an L infinity style term? Right? Is it kind of
sorry, a variance term in which?
In the denominator, you also have this L infinity term, right? That says, if your largest entry is too large, then you.
Right.
Is it of that kind of a flavor, or?
It's a good question. I don't necessarily see it, but maybe.
Also, when you do the rounding independently, you can't guarantee that the total number of open centers is as exactly.
That's true, but that's actually that's okay, because of this, right? Because we have this, right? Because we're in this sort of simplified setting, where you can't really go wrong. Right there, you don't have this issue of like conflict because you're just assigning from one side to the other. So if you don't have quite enough, then you could just add a few more.
Now, what did you open too many?
Yeah, but then if the cost is bounded, then you just take a few away. But open to many is in like not choose enough non-centers.
Yeah.
Yeah. Right, so that's possible, but then you could just overcompensate a little bit by playing with the probabilities, and so that's actually so that's actually not a concern. That works. Okay, so are we done? And I'm the only one who knows what this possibly means. Okay, so why are we not done?
Who's that guy?
So there was this. No, close. No, the late 80s, there was this sitcom, Perfect Strangers, and there was this guy, Alki from the Balkans. And this was like his catchphrase. I just like this so much. And you know, it's like, I don't think anywhere I've given this talk, anyone had any idea what this is. Just amuses me. Okay, so why does what's missing? So what's missing is sort of, I kind of swept this business with this reduction from Charkaret under the rug, but it's actually it doesn't really interact in a black box way with our algorithm. There's no way that you know we could see to sort of just sort of do this clean reduction and say, you know, now this is what we have, and now, you know, every part of our analysis applies cleanly to, you know, to this, and we don't have to worry about what we had before. So you need to actually open the black box and look inside. And to open it just a little bit, but not too much, what I'll say is that what this reduction does is actually it deletes some points, and then it has sort of this initial clustering, and then you only worry about the centers, and then if you have like other points which were deleted, then they get kind of, and their center gets assigned somewhere else, then they get rerouted through the center too, right? So if you have like these white points and they got deleted in the reduction, and then J becomes a non-center and gets assigned to J prime, then these like white points that were assigned to it will also be assigned to J prime, right? But then if you do this reduction, then you have to analyze, right, how this affects the original instance, and then you have to kind of, right, we had all these fancy constraints, then you have to add these fancy constraints to handle these clusters to say like this applies to this, you know, first iteration clustered instance, you know, that we get after the reduction, and not just, you know, just sort of vanilla sort of input the way I presented it before. But these clusters arise in the reduction, right? We run this reduction, this algorithm, using the Convex program in order to know what these clusters are. And now, so we can't just, you know, we can't say, you know, use the Convex program to decide what these clusters are, and now, you know, add constraints from these clusters based on these clusters, right? There's kind of like a circular logic here, right? Because there's no way to know a priori what these clusters in this decomposition are going to be. So what we do is kind of a rounding-based separation of order. So in this sense, we sort of think of like adding constraints for all possible clusterings, but we don't obviously really do that. What we do is we use that Charakarat reduction as a separation oracle, okay? So we run the reduction, and then if we get, and we have this sort of, these constraints in mind for all possible clusterings. If we have a violation of these constraints for the specific clustering that we got in this reduction, in this Charakarat algorithm, then this is a violated constraint. This is a constraint that we could use in the ellipsoid algorithm to say, okay, here's one possible instantiation of this general constraint, which is violated, and we have a separating hyperplane, and we just throw away everything we did so far. We stop the rounding, we add this constraint to the ellipsoid algorithm, and then we try again. Okay, and then, you know, and then this works just like every other, right, algorithm which uses the ellipsoid method with the separation oracle, except that we may have these false starts where we, right, and the point is that we don't need these constraints to hold for the entire universe of every possible clustering. We only need them to hold for the specific clustering that we get in the first stage of our algorithm. So as soon as we get to that point in the ellipsoid method where we can't shrink anymore, and, you know, and we can't have a violated constraint for this specific clustering that we have at hand, then that's all we need. That's all we need to make the rounding go through. Okay. Any questions about this somewhat subtle point? Okay. Right, and then the new constraints are, right, it's, you just take the old constraints and it's exactly the first thing you think of, or maybe the 50th thing you think of, but definitely don't stare at this too much. But it's kind of just taking these clusters and running them through the constraints we had before. Okay, so how much time do I have left?
Around 25 minutes.
Oh, quite a lot.
Sorry.
No, sounds a bit.
Oh, sorry. 10 minutes. 10 minutes.
That's good. Okay. Okay. So just a couple of words on right. So this was like right. Was this question before? Like, you know, what about the, you know, what is the relationship between P and Q? We said, like, you know, well, that kind of motivated it with you know, Q is infinity is like fair clustering, and Q equals P is like globally good clustering, right? So I guess if P is greater than Q, then like this is unfair clustering, like unfair beyond the point of global optimality. So it seems like, you know, maybe a poorly motivated problem, but actually, you know, first of all, it's a natural generalization of the sort of mathematical definition, but it also generalizes other very basic problems. So here's one quick example, which maybe I will run through somewhat quickly, but it's this min S union problem. Right? So this is this problem where you have like a set cover instance. You have like you have a set system, a finite set system, and you have a parameter S, and what you want to do is not cover the universe. What you want to do is actually to cover as few points as possible. You want to choose a specific number of sets from the input so that the union, the cardinality of the union is minimized. Okay, so how does this relate to clustering? This is probably too late in the talk to sort of go through this, but you'll have to believe me that this is exactly infinity one fair clustering. If you kind of plug in the definition from before, right, then the infinity part of the infinity one sort of says that the group cost is going to be one if this group intersects the set of points that we chose as non-centers, and then the one part says that we sum over everything. So we get kind of like an indicator. So we get, these group costs are like indicators for the elements in the union, right? And then the sets are like it's like the reverse. So it's like right, all the points contained in a specific group. I mean, sorry, it's all the groups that contain a specific point. Okay. So I'm bringing this up first of all because right, this we do know quite a bit about this. There's an m to the 1/4 approximation. Roughly, it actually only works when the set sizes are somewhat bounded, but it's still a pretty good approximation for general set sizes. And we also have this sort of conjecture, which is also backed up by like all kinds of integrality gaps and other things, that you can't really do much better than this m to the 1/4. And if you sort of take these same instances from this conjecture and apply it to PQ fair clustering, then you get this lower bound, which is like K, like the target number of clusters, to some constant times 1 over Q minus 1 over P. So you're not going to do much better than that unless there's something very surprising you can do in these like densest K subgraph like problems. And actually, right, and so this algorithm for Binus union, it uses, it does this thing where it kind of guesses some parts of the solution, and because it does this sort of constant number of guesses, if you think of like a convex programming based variant, that convex programming based variant would be like LP hierarchy based. is you need to do this kind of conditioning, like what are the LP values in the event where we like this constant number of elements belongs to the solution. So not this kind of hierarchy, but like Shirali-Adams and things like that. And the issue in kind of porting that intuition to our problem is that they're the kind of events that we condition on. Familiar with these ideas in convex programming hierarchies. Those make a lot of sense when you have like 0-1 problems, kind of like condition on this variable being 1. But for us, the thing that we're conditioning on is costs. It's not a 0-1 thing. So you can do this, but then it requires some complicated discretization. So with where we published this, we had like k to the 1/2 times this thing that I showed before, which we know, or if we wanted to match like minus u should be like 1/4 or somewhere in between. And after that, we were able to bring it down a bit with kind of this, like I said, this discretization or combinatorialization of Shirali-Adams like LPs. And the constraints are even simpler than what I showed before. And this is the actual end of the talk.